We're going to look at 1.4b, which is intermediate value theorem, which, we abbreviate IVT. Squeeze theorem, and then we're going to look more at continuity today. So a couple more properties about continuity. If I have two functions, f and g, and they're continuous at x equals c, then the following functions are also continuous. So if I multiply by a scalar, if I multiply f times g, if I add them or subtract them, f plus g, if I divide, f over g, or f composed of g, which is also like, f of g of x, or whatever value it is, okay? Next, if I have, if f is continuous on a closed interval, and k is any number between f of a and f of b, then there is at least one number c in the closed interval a to b such that f of c is equal to k. And you're like, whoa, lots of mumbo jumbo. Okay, so let's look at this. If I have a function first that is continuous on an interval from a to b, included with the endpoints included. Okay, what it says is that, so f of a, that's the output at a, to f of b, the output at b, there is some number at c, so let's choose a value between these, like c, such that f of c is equal to k, is equal to some value. It's just some value in between these, okay? In between these two outputs. Let's do another one. If I have a function, this one's going to get a little crazier, like so. Let's redo that. Okay. So I'm going to have my function from a to b with endpoints included. And up here, that would be f of a. Down here, that is f of b. Is there some value at c where I get an output of k? So I'm going to make my k value like, okay, so k has to be in between f of a and f of b. So I'm going to go ahead and be like, that's k. No, let's go up here. That's k. How many outputs are there? How many inputs give me an output of k? Well, it looks like 3 inputs right here. So this would be C1, C2, C3. So all we're saying is that if the function is continuous, there's some k value. There's an x value that matches some output in between f of a and f of b. Okay? So let's do an example. Verify that the intermediate value theorem applies to the indicated interval and find the value of c that is guaranteed by the theorem. So we have our function, we have an interval, closed interval, and I want to know what x values give me an output of 0. Okay. So what do I need to do? Well, I'm going to start by looking at what my f of a, this is my a, and my b are. So what are my outputs at f of 0? Okay, that looks like my output is 8. And then what is my output at f of b, my endpoint, which is 3. That's b. When I plug in 3, it looks like I get 9 minus 18 plus 8, which I believe gives me -1. Okay, so f of 3 is equal to -1. So for outputs, I should have an is 0 between -1 and 8. If it is, then there's some x value that should go along with my output of 0. Okay? It guarantees that I'm going to pass through 0, basically. Okay, so because f of x is continuous on the closed interval, from 0 to 3, and -1 is less than or equal to 0, and that's less than or equal to 8. So the k value that I'm evaluating is between my two outputs. Then there exists a c or an x value that is between my closed interval, where f of c is equal to 0 by the intermediate value theorem. So let's find that value. How would I figure out the value of x when y is 0? Well, we just take our function, set f of x equal to 0, plus 8. I'm going to go ahead and big X, so x minus 4 times x minus 2. So I can see that x is equal to 4, or x is equal to 2. But my interval is only between 0 and 3, so my only answer is when x is equal to 2. If the function continued, then we might be able to say that x could equal 4. But right now we can only guarantee that when x is equal to 2, y is equal to 0. So we can say when f of 2 is equal to 0. Why do we care about this? So if the function is continuous, and this function has positive outputs and negative outputs, so is above the x-axis and below the x-axis, then we can conclude that somewhere f of x is equal to 0. So it's like we have zeros somewhere. Okay, so if I had a function like this, a and b, that had negative outputs and positive outputs, at some point I'm going to have to cross over the x-axis and give me a 0. Cool? Yeah, pretty cool. Okay, so the squeeze theorem. If I have three functions where h of x is less than f of x is less than g of x on an open interval containing c, so at some point, except possibly at c itself, and if the limit as x approaches c of h of x equals the limit, and then that limit also equals the limit of x as x approaches c of g of x, then the limit of the middle function as x approaches c of f of x exists and is equal to the limit. So we need a picture. Okay, so if I have a function that is kind of like big, something like this, g of x, and then we have another function like this that's small, like less than g of x. We'll call it h of x. See, g of x is smaller than h of x. And I squeeze in there somewhere another function and we're going to call this f of x. So it's between the two functions in this interval I'm saying forever. Then I know that the limit at a point, I'm going to go ahead and just be like right here. Okay. the limit of h of x is equal to a value, and the limit of g of x is equal to a value. And since they equal the same thing, and I know that f of x is between those two functions, I also know that the limit of f of x is the same. So we can say that the limit of as x approaches c of h of x has to be less than or equal to the limit as x approaches c of f of x, which is equal to the less than or equal to the limit as x approaches c of the largest function g of x. So when they like squeeze together to the same value on the end, we know that the middle function also has a limit that's the same. So we're going to take a look at this example. If I have three functions, 3x is smaller than f of x, and that's smaller than x squared plus 1, for the interval from 0 to 2, evaluate what the limit of f of x is going to be. Okay, so first off, I'm going to need to look at the limit as x approaches 1 of 3x, and I notice that is just 3. And then I'm going to look at the limit of the largest function, and that is of x squared plus 1. And I also notice that is 3. So what I know, that since the limit as x approaches 1 of 3x is less than or equal to the limit as x approaches 1 of f of x, and that's less than or equal to the limit as x approaches 1 of x squared plus 1. And I already evaluated these limits. This one's 3, and this one is 3. So automatically I know that the middle one that's in between these two functions has to also be 3. That's the squeeze theorem. All right, the last thing we're going to look at is continuity of piecewise functions. So when we switch from one equation to the next. So what we're trying to do is, well, I know that sine 2x is continuous for all x's, and then 2x plus something is a line, so that's also continuous over all function or all x values. So what I need to know is, how do I match this up so that when my sine 2x, again, something like this, right, will match up with my 2x plus something. So I need what value here, what do I need to make my k value so that these match up? So what's the x value that I want to evaluate at? First of all, since I know that this goes to pi, you know what, this should also be pi right here. Sorry about that, because this function is less than pi, and we're going to switch to the equation when we go greater than pi. Okay, so I'm going to evaluate what is f of pi, and that's the sine of 2 pi, which is equal to 0. So I want to know, when is this going to equal 0? So I have to plug it into the other equation. So when is 2x plus k going to equal 0? And I go ahead and just solve. I get k is equal to 2x. But then I'm like, wait, I need to evaluate. I'm specifically saying that I want to evaluate at the point when x is equal to pi. So k is going to equal negative 2 pi. So my piecewise function would look like sine of 2x has to be x is less than or equal to pi, and 2x minus 2 pi has to be for x's that are greater than pi. And that's how we make this bad mamma jamma continuous. Last one. So again, what value of k is going to make this continuous? So This one's messed up as well. I don't know what happened here. Okay, so the f of x is equal to 2x squared plus 5x minus 3 all over x squared minus 9 for everything except for when x is equal to 3, negative 3, sorry. And I want to know what k value do I need so that when x is equal to negative 3, that there's no hole or there's no break in my function. Okay? So same, I got to figure out what is, basically I need to figure out what the value at negative 3 is going to be. So the limit. So I'm going to go ahead and say, I'm going to factor the top. I'm going to factor this. So 2x squared plus 5x minus 3 over x squared minus 9 is equal to x minus 3 times x plus 3. The top, I think, is 2x minus 1 times x plus 3. Just double check in my head. Yep, that's right. So that gives me 2x minus 1 over x minus 3. So I notice that now that I don't have the x squared minus 9, I'm only left with the factor of x minus 3. I can actually just take the limit. So what value are we approaching so that I am continuous at x equals negative 3? So how do I make the actual value and the limit value match? When x is approaching negative 3 of 2x minus 1 over x minus 3, I get negative 7 over negative 6, which is 7 over 6, which is equal to k. So that is the value I need so that I don't have a hole. All right, done.